Chapter 7 in your textbook is it's about using the Schrodinger equation to study hydrogen-like atoms. But what a hydrogen-like atom is, so hydrogen-like, is it's a single electron atom with a nucleus. Yeah, so secretly we are studying what's referred to as the two-body central force problem. And we are quantizing it by modeling with Schrodinger's equation. I guess that's a lot of funny talk, but yeah, so we only get to do single electron atoms. Yeah, so it starts off with something kind of strange. Starts with the one-dimensional Coulomb problem. And the way it writes it down is it models with Schrodinger's equation. It's a particle trapped in a one-dimensional Coulomb potential. So it looks like this. So minus h bar squared over 2m d squared by dx squared. So x is the one dimension's name. And then there is a minus. It's e squared over 4 pi epsilon 0. That's the permittivity of free space, with the x downstairs. So the Coulomb potential is normally written down in terms of r because it's written down for three-dimensional space. And that potential is, it's got this e squared over 4 pi epsilon naught. It's the 1 over r potential with a minus sign. And the minus sign is quite important. It just means that as you go out to r, goes out to infinity, the potential goes to 0. And if you're inside r equals infinity, then the potential is negative. So this is it's a bounding potential, but it's kind of like a finite well with an interesting shape. Or actually, scratch the finite well comment. It's because, in a sense, if you take r to 0, this goes down to minus infinity. So the difference between the potential at 0 and the potential at infinity is infinitely big. So I'm not sure where that lies. But anyways, this here is acting upon psi of x, and Schrodinger's equation models this way, psi of x like this. And so you can try to solve this differential equation. It's kind of strange because of that 1 over x business in the potential. But the book shows you that the ground state, so this is the ground state, this particular function works. So this is the ground state. Here's the normalization factor, x e to the minus. So that's the normalization factor. But this right here, this little b that I'm putting there, is multiplying x. So it's got a piece of the function that grows with x, but then is suppressed as x goes out bigger and bigger values. And so you can see that psi 1 of x, in the limit that x gets really big, this heads down to 0. Yeah, so the probability in infinity is going to be 0. So, yeah, but anyways, this is the ground state. It turns out that it works in this differential equation. You can check it. So check that psi 1 of x, this function right here, solves Schrodinger's equation. So I'll put S's equation. That's pretty simple. You just take this thing, put it right there, take two derivatives, multiply by minus h squared, h bar squared over 2m, and then subtract the product of this times that. So, and it will be some number that's independent of the value of x times the very same function. The constant b that sits up there, b has got to have dimensions of inverse distance or inverse length. And the reason is because b times x must have dimensions of 1. You can't have any units for the argument of an exponential, just like the argument of a sine and a cosine and a tangent needs to be an angle. The argument of an exponential needs to have no units. It's got to have dimension of 1. So the dimension of b has to be inverse length. And it turns out that in this problem, with all these details, where I've got the h bar squared, that's the mass of the electron. In the potential, there is the charge of the electron squared, because it's a hydrogen nucleus, so that's a +1 charge in the nucleus, and then an electron that's in orbit around it, that's the -1 electronness of charge. Then there's the epsilon 0. It turns out that B is that great combination of all those things that ends up being exactly the same as 1 divided by the Bohr radius, where the Bohr radius, right, so the Bohr radius is a distance, and so remember we have the dimensions of B needing to be 1 over distance, so here it is, B is a 1 over a distance. So check this out, a sub 0 is 4 pi epsilon 0 h bar squared over mass of the electron times the electron charge squared. So this Bohr radius is there, and it's pretty cool because it's the ultimate combo of the big players. I'm making a joke a little bit, but look at what it depends on. It's got the fundamental mass of the electron, the fundamental charge of the electron. This, if you ever see Planck's constant anywhere, that means that it's a quantum mechanical quantity. Epsilon 0 means we are dealing with electrostatic force or electrostatic potential energy. The pi, that's a geometrical thing about flat space. It's pretty cool quantity in and of itself. And then the number 4 is special. It's interesting that it's there. I don't know. Maybe the number 4 is not necessarily one of the big players, but everything else is a big player. Only thing missing is the square root of -1. But we don't want the distance to be imaginary, so thank you for not being in there. So anyhow, psi 1 of x is a function, and you can normalize it. It's just a couple of calculus steps away. So I won't do the normalization bit, but it is interesting to draw a picture of it. So as described here, let's say that a is taken to be real. So I'm going to solve for it as a real number, and I'm going to use a as a positive number. And then, so I could make some choices like that if I'd like, and so I'm going to. And then it turns out that this function, right, it grows off the bat. Here it's growing, but then it gets suppressed by the dying exponential. So no matter how big x gets, this thing is going to put it back down to the axis and die off like an exponential like this. And that peak happens at roughly a0. So this is as a function of x. Turns out that if you go and you run this on a computer, so computers do things numerically, you can get the first excited state, and it's got a picture that looks more like this. So it's got one sort of wiggle in it. This has sort of got half a wiggle and then dies away. This has got one wiggle and then dies away. And then psi 3, so this is the second excited state. It's got a sharp piece of wiggle, a little bit bigger of a wiggle, and then bigger wiggle, and then dies away like this. This place right here is roughly 5 times a0, and this place right here is roughly 13 times a0. I looked at these in your book. I didn't go do this numerical calculation. But this is what the wave function looks like. So even in this weird toy model, one-dimensional Coulomb potential that's quantized, you get kind of a wiggly behavior in that one dimension. Yeah, so that's how the chapter opens. It's pretty cool, actually.